So continuing where we left last lecture, we were talking about the equations for the orbits. And so the point is that we do have the metric, right? The metric is described by functions a of r and b of r, right? That is what is left of the g mu nu. In fact, in the case of the Schwarzschild solution, they're inversely related to each other. So we have that b of r is equal to 1 minus 2 mg over r and is equal to a to the minus 1 of r, right? And the other thing that we need to solve are the equations of free fall. So we have that the second derivative of x lambda with respect to tau squared plus gamma lambda mu nu dx mu dx nu by d tau is equal to 0. So as we discussed, I think at the end of the last lecture, these equations just reduce to 4 relatively simple equations, right? We have one equation for the r component, one equation for the theta component, one for the phi component, and finally one for the time, right? And well, all the meat, it turns out in the end, lies in the first equation, which is the r1, because in fact the equation for phi gives us that d phi by d tau, right, is times r squared is equal to j squared j is equal to some constant, right? So that is one of the equations. And the TT equations just tells us, the T equation just tells us that dt by d tau, right, is equal to some constant which we're going to call E divided by B of R. So this is some constant again. And it would be too restrictive to take this constant E equal to 1, so we just write it in this way. And so with these two integrals of the motion, we are then left with the remaining equation, which is the one for the R component, which is that A times dr by d tau, right, squared plus j squared over r squared minus e squared over b is equal to some constant, which we take to be minus 1. I mean, in principle, this constant is just some number. But if that number is not equal to 1 or minus 1, then you don't get the correct Newtonian limit, so that number would have to be chosen in that specific way. And it turns out that this is all for material particles. For material particles, because if we are dealing with photons, if the mass is 0, then we have to amend this description a little bit. Because for photons, we have that in this case, d tau is 0, right? So we can't just use d tau as we've done now. So basically, for now, we're talking about particles that have a finite mass, which we call little m. And in fact, it will turn out that if you have photons, then this constant is 0. Right? So this equation as it stands applies to the case of particles that have a finite mass. And I think as we discussed at the very end of the last lecture, we can rewrite this in terms of some effective potential, right? Because we can rewrite this as dr by d tau, putting a 1/2 in front so that it reminds us of a kinetic energy term. So we can write it as dr by d tau plus an effective potential V effective of R is equal to some constant or is equal to 0, right? And so the V effective is just, of course, a combination of this term here multiplied by a to the minus 1. So we can write V effective of R as, now the functions a and b are, of course, given, right? For the Schwarzschild metric, the b is equal to this, and the a is equal to the inverse of that. So we can just plug that in here, right? This is clearly, each one is a function of r, right? And the j square, of course, is a constant, right? So the V effective is equal to minus mg over r, which is a standard Newtonian potential. Then we have the centrifugal barrier term, so plus the j squared over r squared term, right, which is what appears up there already. And then a new correction, which is minus mg times j squared divided by r cubed, right? And then this constant, right, because we choose not to put it up there in this equation explicitly. So the constant, we can add that on, e squared minus 1 divided by 2, right? So as far as we're concerned, of course, the interesting part is the dependence, right, is the dependence of this effective potential on R, but more specifically, it is this term here, right, because this term that is new, right, it is that term that is new. So there is a new term that arises because of the relativistic correction, and so that's what we're going to look at to see what kind of effects it has, and we will see that that term leads to the precession of the perihelion of Mercury. Now, before we do this calculation, let's talk just briefly about two things. One is the shape of the orbits, right? And the other thing that I want to talk about is the potential itself. So let me talk about the potential first, right? That is, we can do a plot of V effective of R, right? So let's just look at the part that depends on R, right? The constant is just a shift. And so it looks V effective, right? Looks like this. So a large R, we have the Newtonian part, so it looks like that. Then it goes up and then it comes down again, right? And so it has a maximum and a minimum, which we indicate by R max is equal to j squared, right, divided by 2mg times the square root, times 1 minus the square root of 1 minus 12 m squared g squared divided by j squared, right? That's one root. And the second root, so that's this r here. And then there is an r min, which is just the other root. So j squared divided by 2mg times 1 plus the square root of 1 minus 12 m squared g squared divided by j squared, right? And so what does that imply is that we have, of course, stable orbits in this region here, right? As long as the particle moves in this region, then it just bounces around like it does in classical Newtonian mechanics. Of course, you notice from this potential that the relativistic correction only picks up at very small r. So in fact, the Newtonian result would be this curve here, and then it would continue up like that, right? So this would be the Newtonian answer. So this is the new part. This is the minus 1 over r cubed term, right? And so that means that, of course, what can happen is that under the right conditions, these two minima and maxima coincide, right? So r min, these two minima coincide, and minimum and maximum coincide, and then this is what happens when r is equal to 6 times mg, right? And so past that, of course, the potential looks like that, right? As a function of r, and you don't have any stable orbits anymore, right? So this r is called the r innermost stable circular orbit. So innermost stable circular orbit. Right? So there is a specific value at which these two maxima and minima coincide, and beyond that you don't have stable orbits. So that, of course, happens at very small radii, right? Because remember that for the sun, the Schwarzschild radius, which is this 2mg, is just 3 kilometers, right? So this is a very small distance scale, right, that you have to go to in order to see this kind of effect. So the other thing that we can talk about is, of course, the shape of the orbit, right? So the shape of the orbit is obtained in the same way that we do in classical mechanics. So if we want to look at the shape of the orbit, right? If you want to look at the shape of the orbit, then you don't want to have r as a function of t or tau, but you want to have the radial coordinate as a function of the angle, right? So you want to have r as a function of, say, the angle phi, right? Or vice versa, phi is a function of r. So that means that we're going to write, say, dr by dt, or dr by d tau, right? We're going to write this as dr by d phi times d phi by d tau, right? And of course, dr by d phi by d tau, remember that r squared times d phi by d tau was equal to j, right? So that means that when we square it, right, because that is what we have in the equations that we wrote down a moment ago, then we are going to pick up a factor, which is this j squared divided by r to the fourth, right? So the equation for the orbit is that a of r, right, divided by r to the fourth, which is that factor over there, right, times dr by d phi, and then squared, right, plus 1 over r squared. So the rest is the same, plus 1 over r squared minus e squared divided by j squared b of r, right? This is going to be equal for massive particles to minus 1 over j squared. And so this equation is very much like what we encounter in classical mechanics when we look at the energy equation, and from that we just integrate the equations of motion and reduce it by quadratures to the angle as a function of the radial coordinates. So that is what we can do here as well, right? We can do the same procedure. It just happens that the kind of potential that we encounter is a little bit more complicated. So in other words, you solve, right, you write dr by d phi. You can write it as, well, the square is going to be something, right, which you can read off from there. And then dr by d phi itself is equal to plus or minus the square root of this expression, right? And then you can write d phi as dr times, if you want still with a plus or minus, right, as dr, right, divided by the square root of whatever you have there. And then you can integrate on both sides, right? And this is going to be some phi minus phi naught, right? And so this is going to be a phi of r, right, minus phi naught. So the procedure to actually integrate this equation and get the shape of the orbit is the standard classical mechanics one, except that the potential here is slightly different. But the nature of the equation is very similar. And so we don't need to really learn any sorts of new tools. The difficulties that one encounters in this case is perhaps doing this integral, right? Because this integral, of course, depends on a of r and b of r, and there's a square root, and so you usually end up with some sort of elliptic integrals. But nevertheless, to figure out what the answer is relatively straightforward, because in most cases, right, we're just interested in weak fields, right? In the solar systems, we can expand out A and B as a function of the first correction, which is 2mg over r. And so let's come to the first application of this stuff, right? And that is the precession of the perihelion of Mercury. So precession of perihelion of Mercury, right? So the equation that we need is precisely this equation over here, right? Right, so let me rewrite that over here on this side. So A divided by r to the 4 times d phi by dr, sorry, dr by d phi squared plus 1 over r squared minus e squared divided by j squared b of r, right, is a function of r, right, is equal to minus 1 over g squared, which is some constant, right? And so to apply this to the precession of the period of Mercury, we need to introduce some notation, right? So we have elliptical orbit to lowest order, at least to 0th order. We just have the standard Keplerian orbit. And so we need to introduce some notation. And so if this is where the focus of the ellipse is, where the sun sits, then we call this distance here r plus, right? The distance from the focus to the perihelion. And the distance from the focus to the aphelion is called r minus, right? And then this distance from the center is called, to this point here, is called A. And the distance from here to here is called E times A. So A is the semi-major axis. And E is the eccentricity. Which tells us how elliptical the orbit is, right? So if the orbit is perfectly circular, then the E is equal to 1, right? So in terms of those parameters, we can rewrite the final result, and we'll come to that in a moment. Nevertheless, at the perihelion or the aphelion, dr by d phi is equal to 0, right? And at that point, of course, the rest has to balance out. So we have 1 over r squared plus minus e squared divided by j squared times the b function at those values, so r plus minus, is equal to this constant, which is minus 1 over j squared, right? And so that allows us, of course, to determine both r plus is equal to something and r minus is equal to something, right? And so the next step is to compute from that the phi function as advertised. So integrate. Right, integrate this equation. So in other words, we take this term here, right? We isolate it, which means we multiplied everything by r to the 4th divided by a. And that will give us dr by d phi when we take the square root, right? And then what we want to have is not dr by d phi, but d phi by dr. So we take the inverse of that. So we're going to end up with the integral of 1 over the square root of something. So we get phi of r minus some phi naught, right? Which you can choose to be, for example, the phi of the r minus, right? And then this is going to be the integral between r minus and r in dr, right, of the square root of a of r divided by r squared, right? So that's just from this term that's being brought over on the other side, and then times 1 over some other square root. So 1 over the square root of the e squared divided by j squared b of r, right, minus 1 over j squared, and then minus 1 over r squared. Right, so remember again that a of r is equal to b to the minus 1 of r, and this is equal to 1 over 1 minus 2 mg over r. So we put that in there, but there is no point in calculating this integral exactly because we're just interested in the leading correction. So the leading correction is going to use just A of r is equal to 1 plus 2 mg over r plus dot dot dot, and B of r is equal to 1 minus 2 mg over r, right? And so we can just put that in there, and then the integration becomes very simple. And then it's a matter of being careful about writing down the correct expression for the angle of precession, right? Because what, of course, is happening is that because of the perturbation, right, because of that j-squared term, the orbit, instead of being elliptical, right, is going to do something like that, right? And so it's going to precess by an angle, right, by an angle which we want, well, we'll give it a name and call it delta phi, right? So for every orbit, the ellipse, the major axis of the ellipse is going to rotate, and the answer for that, the amount by which it rotates is the following, right? Delta phi is equal to 6 pi mg divided by, and if you want, we can put back the speed of light, right? So speed of light, if it's not equal to 1, it goes in there. And then times L, right, where L is just E squared times, is equal to A times 1 minus E squared, right? So Einstein's theory predicts that there is a shift in the perihelion of Mercury, which is given by that amount. Now, it turns out that actually we don't even need to do this calculation, because when you do classical mechanics, you actually go at some point to the exercise of asking the question, how do the Keplerian orbits, for example, get modified when you have a potential, which is V of r, is equal to, say, minus mg divided by r plus some delta V of r, right? So if you have a potential of this type, then if this perturbation is small, then what happens to the perihelion? How does it move, right? And that is, in fact, a standard exercise, and the answer is this, right? So, for example, here is Landau-Lifshitz, classical mechanics, and it's on page 56. The answer is there. So, in other words, you can just take the answer in Landau-Lifshitz. Landau-Lifshitz consider the case where he writes the potential as V of r is equal to alpha times r, or minus alpha times r, plus beta divided by r to the n, right? And so if you do that, you can just use perturbation theory in classical mechanics. And actually, I think this is one of the problems that you do in the first fall quarter classical mechanics class, that you do perturbation theory, right? And for the Keplerian problem. Right, so you can read the answer off. So if you use the answer from Landau-Lifshitz, you get exactly the same result. And what potential do you use? Well, of course, the potential you used is the one we wrote down before, which was this minus j squared over r cube contribution. So now at this stage, of course, well, this agrees pretty well, right? Because you can work out what this answer is, right? Because all you need to know is the mass of the sun, the gravitational constant, and the parameters for the orbit, right? And the parameter for the orbit is known, for example, for Mercury, right? Mercury has a certain amount of eccentricity, which had been determined, a long time ago. I think there were people that already started to do these observations in the early 19th century. And so if you put the parameters in for Mercury, then you find that this delta phi is about 43 arc seconds per century. If you have a very accurate determination of the orbital parameters, then you can do a little bit better than that. And today's number is, so the theory is about 42.98 arc seconds per century. Right? It turns out that in a century, Mercury does about 415 revolutions. You have to, I'm sorry, the precession has to be, that you calculate from this formula has to be multiplied by 415 because there's many times that Mercury goes around like this. And of course, every time it goes around, it accumulates. Right? So the cumulative effect is what is quoted here, and it's for a century. And this agrees pretty well with experiment, right? Because observation gives, and it was known already in Einstein's time that there was this anomaly that the precession of perihelion of Mercury was not entirely explained by all the effects that people knew about at that time. And so delta phi is today is about, the observed value is about 42.45 arc seconds per century again. Right? So these numbers are quite close. The observational value has changed a little bit over the years, right? Because some of it has to do with the fact that in order to determine exactly the amount of precession, you have to choose an inertial reference frame, right? And so what is an inertial reference frame? Well, the Earth, of course, is moving, right? So you could use the center of mass of the solar system and things like that. But actually, the way people do it today is that they choose for an inertial frame something that is fixed by faraway stars, right? So you can use faraway stars to choose a coordinate frame which is not moving at all, right? And well, the stars are moving a little bit as well, right? So just to be safe, what you use is quasars. So you use a constellation of 50-odd quasars, which are very far away, and they don't move that much at all, right? And they're intense sources, so you can use them to fix your coordinate system. So nowadays, when people quote these numbers, right, observational number, they do that by using this rather fancy coordinate systems. Now, it turns out, of course, that already in Einstein's times, right, so around 1916, it was known that there was an effect in the precession of perihelion and Mercury, which was accounted for by the perturbation of the planets, right? One knows that if you look at how Jupiter and Venus and so forth affect the orbit of Mercury, there are some effects which are significant, right? So these are subtracted out. When you look at what's left over, it's these 42 arc seconds per century that is left over, which was unexplained back in 1916. So general relativity accounts for that very well, right? The discrepancy is very small, was already quite small back then. And so this is, in a sense, can be considered as one of the first triumphs of general relativity. Now, what people have done since then is to actually ask the following question, right? Ask the following question. I mean, given that there is this good agreement between theory and experiment, it could be that there's a number of other theories that give also this good agreement, right? So perhaps one should find a way to parameterize things, right? In particular, parameterize the metric. And so nowadays one writes down the following so-called Robertson expansion. Right? Robertson expansion. And the Robertson expansion says, look, okay, maybe general relativity is not completely right. There are some small effects that are due to something else that we don't know and we don't understand. And so let me still write the static isotropic metric as d tau squared is equal to b of r times dt squared minus a of r times dr squared minus r squared times d omega squared, right? Let me still write the metric in this form. And now it is a characteristic of the Schwarzschild solution that, of course, A is equal to B to the minus 1. That follows from the Einstein field equations, right? But, well, maybe we should write it in a slightly more general form. So let me write B of r as 1 minus 2 alpha times mg over r plus 2 beta minus alpha gamma, 2 times beta minus alpha gamma times a correction, which is m squared g squared over r squared plus dot dot dot, right? And similarly, so set, right? And similarly, set a of r is equal to 1 plus 2 gamma times mg over r plus dot dot dot, right? And now, of course, if general relativity is correct, right, if Einstein's theory is correct, then it's only one answer, right? So in GR, you have alpha equal beta equal gamma is equal to 1, right? So in general relativity, all those coefficients are fixed, but nevertheless, there could be something that we don't know and we don't understand by which these coefficients are not quite equal, right? And so the Robertson expansion relies on these 3 different numbers, right? And so deviations from general relativity are then specified in terms of deviations in alpha, beta, and gamma from unity, right? Now, in particular, there is, of course, a candidate for an extended theory of gravity, right? The candidate for an extended theory of gravity is the theory that was proposed by Jordan, Brans, and Dickey, right? Because in the Brans-Dickey theory, you have this scalar, right? You have this additional degree of freedom, which is the scalar, and well, there's a good motivation for considering something like that, and scalar theories, scalar tensor theories are still popular to this day, and so in scalar tensor theories, you don't have alpha equal beta equal gamma equal to 1, right? So, for example, so in the Einstein case, we have alpha equal beta equal gamma equal to 1. And in the Brans-Dickey theory, you have some deviation from it, which is that, in fact, alpha and beta are equal to 1, but gamma is equal to this Brans-Dickey parameter omega, 1 plus omega divided by 2 plus omega. Right, so this is different from 1. Different from 1. So that means that if you do fairly accurate experiments, you can determine whether actually the Brans-Dickey theory has some validity, whether it should be taken seriously, right? And so that already applies, of course, to the precession of the perihelion of Mercury, because now you can recalculate. It's very simple, right? Because you do the same calculation we've done here. The only thing that changes at the end is the form of the function a and b when you do the integral. When you do the integral, you have to put those in. And so it's just a couple of lines of algebra. And so then you have that the precession of the perihelion of Mercury, the angle is equal per orbit is 6 pi, is the Einstein value, which is 6 pi gm divided by this quantity L, c squared L, right? L was equal to the semi-major axis time 1 minus the eccentricity parameter, and then times some function that depends on alpha, beta, and gamma, and that function is 1 over 3 times 2 plus 2 gamma minus beta. 2 gamma minus beta, like this. Right. So that means that by looking again at the precession of the perihelion data, with the magnifying glass, right, looking at precisely all possible effects, then you can determine whether actually the agreement with GR is so good. And in particular, you could have that this number here itself is very close to 3, but nevertheless there is maybe some cancellation between the various coefficients, right? So we'll come back to that in a little bit, right, because we actually want to discuss another case where you can test GR and also extract this alpha and beta and gamma parameters, which is the deflection of light by the sun, right? Right. Before I complete this discussion, let me mention one more thing, that is that you can look at other planets, right? It turns out that Mercury, because it is so close to the sun, has the largest effect, right? But one can look at Venus, right? And the prediction for Venus, right? So you can make a table where you have the theoretical prediction and the experimental number, right? And for Venus, the theoretical prediction is 8.6 arc seconds per century again, right? And the experimental number is 8.4 plus or minus 4.8. At least this is what is quoted in Weinberg. I think there might be some better numbers. And for the Earth, the correction is even smaller, right? Because it gets further away. So it's 3.8. So we can see that it's almost an order of magnitude smaller than Mercury, right? That's the reason why we do like to look at Mercury. And the observational number is 5.0 plus or minus 1.2. And so the only chance to get an effect which is significant for a body that is further away from the sun is to have a very large eccentricity, right? And so there is actually an asteroid which is Icarus, which does have a rather large eccentricity. And for Icarus, the effect is 10.3, and it's been measured about 9.8, plus or minus 0.8, right? But so that points to the fact that doing precision experiments about the precession of the perihelion is not going to be easy to do unless we have a body that is very close to the sun, like Mercury. And even for Mercury, of course, there is the difficulty of estimating precisely what the other effects are that you need to subtract out from the total answer to just get the relativistic correction due to Einstein's theory, right? And so we'll come to that in a little bit when we do a kind of a summary. In particular, there's also the issue of the oblateness of the sun, which I mentioned in the last lecture, right? The sun is not a perfect spherical body. It has a non-vanishing quadrupole moment. So that gives a small effect as well, and it has to be taken into account. But all these things have been done over the years, and the numbers have become better and better. So before we do kind of a summary of how good GR is as it compares to the observational numbers in the solar system, let me talk about photon orbits. Right. So repeat for photon orbits. Right. Repeat for photon orbits. So now, again, the mass of the photon is 0, right? M is equal to 0. So that means that d tau squared is equal to 0. So we can't use the d tau as a parameter in the equation for free fall. This is something that we discussed some time ago. And so instead we use some other parameter, which we call p, which is referred to as an affine parameter. Right? Well, that doesn't really cause any difficulties, because basically what it amounts to is having everywhere, instead of the tau, having the p, right? And so the p is a parameter that just tells us how far along we are on the trajectory of a particle, right? And so we go back and look at the equation for free fall, or even more simply, we can look at the metric. Right? It turns out that there's actually a shortcut. There is a shortcut, and it's a nice exercise to use this shortcut to actually get the same kind of equations that we got before. It works both when the particle is massive and when the particle has 0 mass. So the shortcut is to look at the metric, or the d tau squared. Right now, for a photon, that of course is equal to 0. But nevertheless, in the Schwarzschild coordinate system, this is equal to b of r times dt squared minus, right, a of r times dr squared minus r squared times the omega squared. Right? So that's certainly true still, except that we have a 0 here. Right? And of course, what we can do at this point, right, is first of all, we consider orbits that are equatorial. as we did before. So we consider the case where d theta is equal to 0 and theta is equal to pi over 2. Right? So we restrict ourselves to the equator. And so that means that we now have that 0, right, is equal to b of r. Now we introduce this affine parameter, and we divide out through it. So we write this as dt by dp squared. Right? If the particle was massive, we could just divide dt by d tau, and that would be fine. And we get the equations that we discussed before by this method. But here we have this dp, right? And then we have minus a of r, and we have dr by dp squared. So dr by dp squared, right? And then minus r squared d phi by dp, and that is again squared, right? And that is all there is to it. Now we still have one of the integrals of the motion, right, which was the fact that r squared times d phi by dp is equal to j, right? So that's going to be used in here, right? There's still, remember, the equations for free fall are basically the same, right? When you have a particle that has a mass or doesn't have a mass, you just have to use this other parameter p, but otherwise the equations are identical. So that means that the constants of motion are the same, and that means that we can replace that by a constant times some power of r squared, right? And so we rearrange things slightly. Right? So the other thing we want to use is the other constant of the motion is that dt by dp. Remember, we had that before as well, except we had dt by d tau is equal to e over b, and here we have dt by dp, which is e over b of r. Right? So that goes in there as well. So one constant of the motion, second constant of the motion, and that leaves us with b times e over b squared. That's the first term, minus a, and then dp by dr, and then squared, sorry, dr by dp. Getting ahead of myself, dr by dp squared, and then minus r squared, and then j divided by r squared, and then squared. And this is equal to 0 because we are dealing with a photon for which the d tau squared is equal to 0. Right? So in particular, well, this of course looks very similar to the equation we had before, but the difference is that there is a 0 here where there was a constant before. Right? And so now we divide this by a. Right? We want to kind of isolate this kinetic term, so we write it as dr by dp, right? And then squared, and plus the rest, which is minus 1 over a, e squared divided by b, plus j squared divided by ar squared is equal to 0. Is equal to 0, right? And so that's very similar to the equation we had before for the potential, right? Because we can now write this also in terms of some potential, right? And the potential is actually going to look different from what it was in the case of a particle of finite mass, right? Because we rewrite this as right, we write this as dr by dp squared plus 1 over a, right, times j squared over r squared is equal to some constant. So we put the constant over on this side, right? And then now we divide by j squared. Of course, j is a constant too, right? So we divide by j squared, 1 over j squared dr by dp. It's convenient to write it in this form, and then plus some effective potential, right, which depends on r, right? And that is going to be equal to e squared over j squared, which is some other constant, right? We can call that b squared, for example, right? And so the V effective in this case, right, is essentially a combination of this, the A and the R squared term, so is equal to 1 over AR squared times R squared, right? And so we use the expression for R, and so this is equal to 1 over R squared, 1 plus 2mg minus 2mg over R. And that's it, right? And that's it. So there is an effective potential in this case too, right? If we try to write it in terms of a classical mechanics expression for the energy, we can do that, but the potential is actually a little bit simpler than what we had in the case of finite mass, right? Because if we plot it, V effective of R is a function of R, right? Then we notice that the shape is just like that. Right? The shape is just like that. Right? So there is a maximum here, which corresponds to R naught equal 3 mg. Right? And then for small r, again, we have a 1 over r cubed minus 1 over r cubed dependence. So that means that there are 3 types of orbits. There are 3 types of orbits, right? So the first one is the orbit that we can have when the distance is greater than this amount, right? And so one is this. So that's the case where you have the sun here, right? And the orbit is just like that. Well, it doesn't have to get too close, right? So it's an orbit of this type, right? And so that is what happens out here. Okay? Now, if the energy is just right and the particle sits on this maximum, then of course you can have a stable orbit, right? So for a photon, you can have an orbit like this, and I say it's stable, but it's actually not stable. It's highly unstable because it is at this, exactly at this point here, right? So this is unstable. And it happens at just one distance, right? And that distance is the R naught equal 3 mg. And the third possibility is that you are over on this side so that the distance is less than this 3 mg. And of course, in that case, and I'm kind of running out of space, but in that case, the particle just plunges into the origin. The photon plunges into the origin. So in the third case, you just have that the orbit looks like that. Right? The orbit looks like that. Right. So clearly that is different, right? Different from the case of a material particle, right? We saw that in the case of a material particle, we can have nice stable orbits as long as the radius is large enough. That cannot happen for a photon, right? So photons cannot go around orbiting the solar system, right? That is something that within the framework of general relativity is not possible, right? There is only one circular orbit which is allowed, which is precisely at that radius, and that happens to be unstable, right? And so presumably the same thing applies to larger bodies as well, right, beyond the solar system. Even if you look at the galaxy, right, you would imagine that if you have a distribution of mass which is spherical, more or less, that is described by something that looks like the Schwarzschild geometry, then these photons will not easily orbit, right, will not easily orbit around, and they will have instead one of those 3 types of behavior, right, with the intermediate one being just for one very specific radius and therefore kind of unstable to any sort of perturbations, right? So that is as much as we can say at this point on the orbits themselves. Now notice that we did not expand anything, right? The result is kind of exact, right? We just used the exact form for A and B, and that's what comes out of it, right? So now the next thing is to look at the deflection of light by the sun and see what one gets from the same type of equation, the equation that we already have over on that side, right? So deflection of light by the sun, right? That was another major prediction by Einstein's theory. So the picture we want to draw here is one where we have the sun, right? And then light comes in, say from a distant star, right? And it comes in, and as a consequence of the effects of gravity, its path is deflected in this way, right? And so this is clearly a problem of orbits, again, except that it's not a bound orbit, but it's just kind of a scattering problem, right? So we have an angle at infinity, right, when the light first comes in. And then if you continue this on a straight path, then when the light comes out, right, it comes out a different angle. And so this angle is what we would describe as delta phi, right? And in order to describe the amount of deflection, I think there's certain quantities that should be introduced here. One is usually the impact parameter b, right, which is this distance, or the distance of closest approach, which is this r naught. And the two, of course, are very close to each other, almost the same number, right? Clearly, to maximize the effects, you want the light to be as close to the surface of the sun as you can. Of course, if light goes by the surface of the sun, the light from a distant star, then generally you won't see it. But of course, if you have an eclipse, then you will, right? Because the sun will be obscured, and finally you'll be able to see the star, and by how much it actually moves in the sky because of the deflection of light. So how does one calculate something like this? Well, the calculation, again, is fairly straightforward and requires the equation for the orbits, right? So we start out with, I think, what we have, for example, up here, right? Right, so dr by dp squared minus 1 over a times e squared over b is equal to, plus j squared divided by a r squared is equal to 0. Right, so to get the equation for the orbit, we do the same trick we did a moment ago when we discussed the precession of perihelion Mercury. So we write dr by dp as dr by dt and dt by dp. Right? Sorry, that's not what I mean. We're going to write in terms of the angle. dr by d phi and d phi by dp. Right? And so we use for d phi by dp, we use the fact that r squared times d phi by dp is equal to j. Right, so this term here, when you square it, gives us j squared divided by r to the 4th. Right, so we can rearrange everything and isolate the dr by d phi term. Right. So isolate the dr by d phi term. Write the square of this plus the rest. So minus e to the 4th, r to the 4th, divided by a. Right, so we get this r squared here squared, and so the 1 over a that we had there, and times e squared divided by bj squared minus 1 over r squared is equal to 0. Okay, very good. So the other thing is that from that equation, we also get dr naught, because at r naught, dr by d phi is equal to 0, right? So that is 0 at dr naught, right? And therefore, at r naught, this whole thing has to be equal to 0, right? Right? So we can solve that because, of course, what has to be 0 is the expression in parentheses, right? So that tells us that J is equal to E times R naught times 1 over the square root of B of R naught, right? So that determines the R naught, right? So now we take the square root of this, so dr by d phi is equal to plus or minus the square root of r to the fourth divided by a times the square root of the whole thing, e squared divided by b, j squared minus 1 over r squared, and then square root of that, right? And then we integrate, so we write the integral in d phi is equal to the integral in dr times 1 over this expression that we have here, right? And then integrate that. And that's very much similar to what we had in the case of the precession of perihelion of Mercury. So you do the integral. Again, you use the weak field limit. So expand again, right? Expand to do these integrals. Expand a of r is equal to 1 plus 2 mg over r plus dot dot dot, and b of r is equal to 1 minus 2 mg over r. Right? So when you expand it out, then the integral is fairly doable. And the answer is as follows, that delta phi is equal to 4 mg divided by r naught, the distance of closest approach, which is basically the diameter of the sun, right? And if you put the speed of light, then you get a c squared here as well, right? And then, so plus terms, which are of order m squared g squared over r naught squared. So these corrections are small. Remember that the distance scale associated with mg, right? 2 mg for the sun is 3 kilometers, right? So this is a very small distance divided by a fairly large one, because the diameter of the sun, actually the radius of the sun, is about 0.64 times 10 to the 6 kilometers. So we're talking about 1 million kilometers versus 3 kilometers. So this is a very small angle, right? And now, if you do have this Robertson expansion, then there's going to be a coefficient in front, which is 1 plus gamma divided by 2, right? So Robertson expansion, right? And so that, of course, is kind of interesting because it tells us that the deflection of light by the sun is just sensitive to gamma only. Now, if you remember, the precession of perihelion Mercury was actually sensitive to 2 of those Robertson parameters. But here we have just 1. So the deflection of light is a direct measurement of gamma. And so the prediction, right, from, of course, in Einstein's theory, gamma is 1, right? So Einstein's prediction is that this deflection, delta phi, is 1.75 arc seconds for a grazing, for a light ray that passes right next to the surface of the sun. And now, this is something that is not easy to measure, right? You need a solar eclipse, and the first one to measure this was Eddington in 1919, right? So the prediction by Einstein was in 1916. So Einstein predicted that there would be such an effect. He actually predicted that the light would be deflected by the sun already in 1911, but in 1911 he did not have the full theory. So in 1911 he predicted that the deflection of light would be half of that, right? So later on, when he had the full equations, then he realized that it would be twice as big. And so in 1916 the prediction was that it would be 1.75 arc seconds. And well, in 1916, the First World War was going on, so there was no way that anybody could do a measurement because you had to track down a solar eclipse somewhere around the globe. And well, traveling was not something that you could do easily back in those days. But when the war was over, Eddington packed up all his stuff and went to Brazil because there was a solar eclipse that was predicted. So he took with him all his photographic plates and stuff, and he actually looked at how much the stars moved around. The theory predicts, of course, this angle if it's very close, and then if the stars are further away from the surface of the sun, then there is a precise prediction as well on how much they should be deflected. So he compared the theory with the experiment and came back saying that this was a brilliant verification of Einstein theory, that the deflection was exactly what Einstein had predicted. So that was back in 1919. Eddington came up with an observational number which was about 1.75. I think those numbers were later reanalyzed in the sense that people did more observations and found out that maybe, it was certainly in the right ballpark, but maybe, so observation. Delta phi is around 1.70 maybe. That order, right? There is a substantial uncertainty. I mean, it is not the kind of measurement where you can go down to fractions of a percent because of the difficulty of doing the observation and the fact that even when you have a total solar eclipse, there's still quite a bit of bright light. And in any case, you're dealing with rather small statistics because you're looking at just those few stars that are in the right location at that time and see by how much they move. So it is not, it could not, I think, be regarded as a high precision experiment. But nevertheless, nowadays we know that if you look at the night sky in the evening, it's affected by the sun. Right? The location of the stars is actually slightly off because of this effect, right? And so there is a European Space Agency satellite that has gone up, which is called Hipparcos. And what Hipparcos is doing, instead of looking at just a few stars like Eddington did, it looks at 10 to the 5 stars. So if you're looking at 10 to the 5 stars, then you'd start to have a significant statistics. And with that significant statistics, now you can get better numbers. So the hope is that even these kind of experiments are going to become more precise as times goes by. And of course, gravitational lensing, right, is just the same story pretty much, right? Gravitational lensing has to do again with the deflection of light past a heavy body. So that heavy body doesn't have to be the sun. It can be some faraway galaxy, and the source of the light itself could be some other galaxy. Whatever luminous object is past it, right? And in fact, you can even have binaries where one of the two is emitting something, say, for example, radio waves, and the other one is going to deflect that. So there's a number of different instances where the same kind of calculations can be done, and you can obtain useful results to test GR. And well, as far as we know, everything agrees with GR at this point within observational errors. Now, let me mention briefly another related type of prediction and observation that comes out of the same type of equations, right? In fact, the same equation we have over there, which is radar echo delay. Radar echo delay. So in other words, in order to look at this deflection of light, you don't need light, right? You don't need light. It's good to have anything that's a photon, right? And so that includes any sort of electromagnetic radiation, including radio waves, right? And so the equations are, of course, the same, right? Same equations as before. Except now we're looking at timing differences, right? So we're looking at timing differences. And so that means that our equation will not involve the dr by d phi, which has to do with the orbit, but has to involve the time at some point. So the equation is, you can read it off from what we had a moment ago on the blackboard, right? Which is that a divided by b squared is equal times dr by dt, right? Squared plus j squared over r squared minus e squared over b is equal to 0. Right? That's the equation we need. And first of all, we have a 0 here because we're dealing with light again, right? Even though it's radio waves, but still electromagnetic radiation corresponding to particles which have zero mass. The other thing that you notice is that we have the dt, right, dt. And the reason for that is that, of course, initially we have dr by dp, which is this affine parameter, right? And, but dr by dp can be written as dr by dt, which was what we have up there, times dt by dp, right? Right. But this quantity here is just equal to E divided by B of R, right? And so that gets squared. And so that accounts for this factor here. That accounts for that factor here. So by using the time, and notice that the affine parameter is gone, right? Because it's replaced by E over B. So by having the time, we pick up this extra factor of E squared over B squared, right? And so now we have to go again through the exercise of calculating from the geometry of the situation how much of this time delay we have, because the idea is as follows, that you have the sun over here, right? And we have the Earth on one side, right? So we have the Earth over here, right? And now we need this radio signal to go past the sun, right? So it gets deflected. And so over on this side, it would be very convenient to have another object that we can talk to. And so that would be, for example, Mercury, right? And now if radio waves go over to Mercury, right, like this, then they will be, again, deflected by the sun, right? Using exactly the same formulas that we wrote down before for the deflection of photons, light photons, right? And in fact, the thing then can come back also the other side, and we have same story, that it gets deflected like this, right? And so you need an object that refracts these radio waves, right? And of course, ideally, you would like to have a mirror, right? But you can't have a mirror over here. You're going to have an object that instead of looking like a mirror is looking more like a bumpy sphere. It's not a particularly good reflector, so there's all sorts of systematics that you have to worry about in actually being able to track down what this delay looks like. But nevertheless, you can imagine, at least when it comes to the theoretical prediction, of course, what you're going to do again is isolate the dr by dt term, right? Dr by dt is going to be equal to plus or minus times the square root of something, and then write dt is equal to dr times 1 over the square root, and then integrate on both sides, and this will be t minus t naught, right? So the procedure to do this calculation is the same, right, as we have done before. And what appears in the square root is everything that we have over on, in particular, this quantity here multiplied by b squared divided by a and e squared. Right, so let me skip the details and just, again, of course, a of r is going to be replaced by the 1 plus 2 mg over r, or whatever comes out of the Robertson expansion, which would have this gamma, etc., right? So the answer, and you can read a little bit more about it in Weinberg, is a couple of lines where we write out the integral and calculate it in this weak field limit. The answer is that for this time delay, you have that delta t is equal to 4 mg, right, the relativistic delay, times 1 plus a correction, which in the Robertson expansion again involves gamma only, right? That is not surprising because, of course, we already seen that for the deflection of light by the sun, it's just gamma that comes in, and this is pretty much the same story, right? So you expect, again, just gamma only, times, and now we have a log of various distances, right? The distances, of course, that will come in is, say, the distance to the Earth from the center of the sun, and the distance to Mercury, right, which we call Rm, where m is here stands for Mercury. And the Shapiro formula is that this is equal to 2Re times Rm divided by r squared, which is r squared being just a sun radius. Right, and then plus, of course, higher order corrections, which we don't care about. And so if you set gamma equal to 1, then you get delta t, right? Again, from the orbital parameter, distance of Mercury, distance of Earth from the sun, the radius of the sun, and so forth, which is pretty much well known. This is about 240 microseconds, right? And so that is a small delay, but it's significant. And electronics already back in 1976 had no problem in determining such a delay. I mean, it was already quite a measurable number. It takes about 20 minutes for the signal to go to Mercury and come back, right? So that's a long time, right? T total is about 20 minutes. Right? So it's a small effect, but nevertheless it is measurable. And so again, this can be used to determine whether, indeed general relativity is correct, whether gamma is close to 1 or not, right? Well, it turns out, of course, that since then, right, since Weinberg discussed this kind of setup in the book, there have been other missions, right? And perhaps the most useful and important one is where you have something that's really far away, and that is emitting radio waves, and that would be the Cassini mission to Saturn, right? So the Cassini spacecraft, which was launched, I believe, in 2003. So Cassini mission to Saturn, right? It was 2003. Girolamo Cassini happened to be an Italian astronomer who's actually the first guy to actually see with a good quality telescope. What did he see? He saw, of course, the Cassini division. Right? What's the Cassini division? The fact that the rings of Saturn, there's a gap. Right? There's a nice gap. He was the first one to see it, right? And so that's why the mission to Saturn was called the Cassini mission. And so what the Cassini spacecraft has, right, here's the spacecraft, right? It has a very nice antenna like this, right? And, well, I should orient it maybe the other way, right? Put it like this. So it has a nice dish like that, right? And it sends radio waves, right? And provided it's in the right location, this thing goes by the sun, right? It goes by the sun, right? And we're out here somewhere, right? Right? And so that, of course, starts to be a much cleaner experiment, much cleaner because we don't have to rely on the reflectivity properties of Mercury, right? Which introduces all sorts of systematics. Here we have a well-defined signal that is sent out on whatever band it's supposed to be, and a nice monochromatic radio wave that gets sent over, and so it's very controlled. And so the result of the Cassini mission is actually that, what does it determine? Well, of course it determines gamma, right? Now we have a very clean handle on gamma, which is much better than deflection of light by the sun from various stars, and gamma is constrained from the Cassini mission to be, so it's usually quoted as the deviation of gamma from the GR value, which is 1, and so it's 2.1 plus or minus 2.3, right, times 10 to the minus 5. So now that starts to be a lot more precise, right? A lot more precise, right? So that is a very nice result that constrains this gamma significantly, and so again, radar echo delay, or the deflection of light by the sun, the leading term contains gamma only, right? Contains gamma only. So that means that now we can go back at what? Well, go back at the other observations that involve the other Robertson parameters, in particular the precession of the perihelion of Mercury, right? So go back to the precession of the perihelion of Mercury, right? Because now we think we have a good handle of what gamma should be, right? And so this is the review by Cliff Will, which is April 2014, right? A few weeks old. And he writes down that the delta phi, due to the precession, right, the general relativistic precession of the perihelion of Mercury, can be written in this form as 42.98 arcseconds per century, and that is the GR answer. Right, and the GR answer was, remember, was equal to 6 pi gm divided by the radius of the sun. Sorry, divided by c squared times a squared, a times 1 minus e squared, times this semi-major axis and the eccentricity, and times the corrections that come from these Robertson parameters. So the Robertson expansion gives a coefficient which I wrote down already before, which is 1/3 of 2 plus 2 gamma minus beta, right? And now in here we're going to use, right, what they use is this value. Right? Use this value, and that will now constrain beta. So use gamma from, say, Cassini, right? And so that now gives beta, provided we have, of course, a very accurate determination of what the true precession of the perihelion of Mercury is. Nevertheless, there is also an effect which I mentioned before due to the oblateness of the sun. And the effect of the oblateness of the sun can be calculated. It's 3 times 10 to the minus 4 times the quadrupole moment of the Earth contributes a factor which is J2 divided by 10 to the minus 7. It is a small number, but nevertheless, that number is estimated in the right units to be about 10 to the minus 7, which means that this expression in parentheses is of order 1, which means that on the whole balance, the oblateness of the sun only contributes something of the order of 10 to the minus 4, which is a fairly small correction, and then close parentheses, right? So because this effect is small, this constrains basically beta directly. So one finds that beta is, as a result, well, let's say beta minus 1 is equal to, the best number nowadays is minus 4.1 plus or minus 7.8 times 10 to the minus 5. And I guess that would include this correction as well. The best estimate one has nowadays for the oblateness of the sun. The shape of the sun apparently can be measured quite accurately based on heliosismology. That is, on how, you know, the sun itself behaves when it moves around, when the interior is moving like in an earthquake. So anyhow, this is the best one can do nowadays. So the conclusion, of course, which is not entirely unexpected based on what we discussed in this class, is that general relativity does pretty well, that these relatively straightforward tests of general relativity on solar system scales, which have to do with precessions and with photon orbits and radar echo delay and so forth, constrain the gamma and beta to be within the general relativity predictions to something, a correction of the order of 10 to the minus 5 or so, which is pretty good. So general relativity passes the test quite well. Now, let me remind you also that that tends to rule out the Brans-Dicke theory, right? Because in the Brans-Dicke theory, we have, if you look at the Brans-Dicke theory, right, that predicts that alpha, I think I wrote that down before, alpha is equal to beta is equal to 1, and gamma is equal to 1 plus omega divided by 2 plus omega, right? So the Brans-Dicke theory, in its, scalar tensor theories in their simplest implementation, like in the form of the Brans-Dicke theory, do have a problem, right? They do have a problem already on solar system scales because gamma, by now, is pretty strongly constrained, right? Gamma is very close to unity, and so this omega, of course, when omega is very large, gamma approaches 1 in Brans-Dicke theory, right? So that would say that the omega in the Brans-Dicke theory has to be fairly large, otherwise you would have detected deviations and you would have seen some evidence for this Brans-Dicke scalar, right? So the Brans-Dicke scalar either is not there or it's hiding very well, so that at this point we just don't see it, right? And so I think we're out of time. So next time we're going to discuss the weak field limit. That is going to be very interesting because we're going to look at Einstein's field equations in the limit in which the metric is close to flat, right? In which you can write the metric as an eta mu nu plus a small correction, and then you can expand everything out. It becomes a linear theory, and you get gravitational waves, right? So that's what we're going to discuss next time. So any questions or comments? Yes?
What changes do you have to make for a rotating neutron stars, binary?
Yes.
What differences do you need to?
No, I think it's very similar, right? I mean, you are dealing still with a problem in orbital motion, right? You can actually go a long way by just considering the fact that you have a correction to the Newtonian potential, which is this 1 over r cubed, right? Of course, when you have a binary neutron star, you don't have one heavy object which is basically static at the origin, right? You have a two-body problem that has to be discussed in terms of reduced mass effects and things like that. But the equations are all there. I mean, there is really no new physics that you have to include, right? And so, yes. Any other questions or comments? All right, well, I'll see you Thursday then.